Okay, welcome back to lecture 25.2, where I want to talk about, let's talk about superfluidity. And actually this superfluidity and superconductivity are basically the same thing, okay? So last time we led into this by saying that there's a class of phase transitions called second order phase transitions. Magnetism is one second order phase transition, but superconductivity and superfluidity are another. And so we've talked a little bit about superconductivity and how superconductivity and superfluidity are driven primarily by the third law of thermodynamics, right? That is that we want the heat capacity to go to zero as fast as we can as T goes to zero, right? So that our entropy goes to zero as fast as we can. Okay, so I want to talk. You can think about superconductivity as sort of a case of superfluidity. So it's we'll talk about superfluidity in general. Okay. So there's a lot of these ideas that there's two kinds of people in the world, right? There's the people that eat good bananas and people that eat bad bananas, right? Like yellow ones and brown ones, whatever. There's all these like arbitrary groupings of things in the universe and people, but there is one that's actually very true. There are two kinds of particles. Two kinds of particles in the world. There are bosons and there are fermions. So this is after Bose and this is after Fermi. Okay, so hopefully you heard this in second year modern physics, but if you didn't, then this is sort of a reminder. So bosons are things that are really even, fully symmetric, and fermions are things that are odd. They obey the Pauli exclusion principle. Okay, so let's imagine the quantum harmonic oscillator. Okay, so hopefully in second year physics, or in quantum, you did the quantum harmonic oscillator, and you remember that the energies in the quantum harmonic oscillator versus whatever variable, say position, have a parabolic energy distribution, right? Where the classical harmonic oscillator, right? This is a energy versus x. This would be 1/2 kx squared, right? Or this could be momentum, right? This would be 1/2 or p squared over 2m. So in either of our variables, momentum or in position, this is quadratic. Usually it's in terms of energy versus momentum, and then this is called a dispersion relation. Okay, so that's just a term you'll hear later. So this is the dispersion relation for a harmonic oscillator, but when you do a quantum harmonic oscillator, you find that there's no longer there's no longer a continuum energies, there's a discrete energy levels. So the first one lies at 1/2 h bar omega, but that the separation between these all are h bar omega, right? So hopefully you saw that. So this one is called the ground state. Okay, so this is the lowest energy, but it's not zero energy. There's always this finite energy in the quantum harmonic oscillator, and that's called the 0 point energy. So the 0 point energy. All right, so Now, when I lower the temperature of a system, right? So as the temperature goes to 0, what you can do is you would reduce the thermal energy in a system in a quantum harmonic oscillator, and you'd imagine that your particles would enter successively lower and lower energy levels. And for bosons, they all can enter the ground state. Okay. So this is an interesting, and this is called the Bose-Einstein condensation, when a significant fraction of these enter in the quantum ground state. So you'll actually work out the conditions for a Bose-Einstein condensate and this phase transition into a Bose-Einstein condensate in in 311 in StatMath. So we won't do that here, but just to imagine that all of the various particles can occupy these ground states, right? So they can all reside here. And this actually results in superfluidity. Okay, why is that? So if we remember back to your second year, you had the de Broglie wavelength. Remember what that was? That was lambda was h over p. Right? So what happens is as the temperature goes down, the momentum also goes down. It actually doesn't go to 0, it goes to some finite value, but it goes down. And then our de Broglie wavelength goes up. So I have a very nice graphic on how as the temperature is lowered, the de Broglie wavelength for these quantum mechanical particles, as they go further and further down in energy, actually get larger and larger and larger.
So this is a nice image that I've taken from Wolfgang Ketterle at MIT, who is one of the discoverers of the Bose-Einstein condensation in cold atomic gases. So you can see that exactly at high temperatures, it's what we know to be the classical laws of physics, that atoms are behaving like billiard balls. That is, their de Broglie wavelength is small compared to any other length scale in the problem. But as that you lower the temperature, the de Broglie wavelength can grow. So you would have this quantum mechanical matter wave packets. And the Bose-Einstein condensation is when these matter waves are so large that they're starting to overlap. And then at t equals 0, we basically have all of these waves, these wave packets, in the single ground state. And that's the pure Bose condensed state, this giant matter wave. And so superfluidity is sort of this big red bar where you can see there's a macroscopic wave function which is on the length scale of your sample size. And so this is this shorting of what happens in superconductivity and the flow without resistance in superfluidity.
And you can basically think of this as your wave on a string problem. Right? So when you had a wave on a string in first year physics, you have all these different modes that are possible. But when you're in your quantum ground state, you only have one possible mode for your waves on your string, and that's the quantum ground state. And what it means is that across the entire sample volume, or here across the entire string, there's only a single macroscopic wave function. And that single macroscopic wave function means that any portion of the macroscopic vessel of a superfluid is physically connected, right? And so in superconductivity, what this means is you basically have an electrical short, right? The left and right hand side of your sample are identical. So with a superfluid, it means that you have flow without resistance. You have flow of electrons. It's actually not exactly electrons, and I'll tell you a little bit more about that in a superconductor. But in a superfluid, it really means that it's a neutral particle. It really is the atoms, okay? So a very good example of a superfluid, there's two isotopes of helium. Helium-4 and helium-3. And so we actually studied both of these in my group. Helium-4 is a boson, and helium-3 is a fermion. Okay? So these bosons can all Bose-condense into this quantum ground state and can form a macroscopic wave function. And so the TC of helium-4 is 2.17 Kelvin. It's got 2 protons, 2 neutrons, 2 electrons. It's fully even, right? It's an even particle. And so this is something we call a composite boson. Now helium-3, on the other hand, has 2 protons but only has 1 neutron, so it's actually a fermion. It's got an odd number of neutrons. And so it can't Bose-condense. If you go back and think about the quantum harmonic oscillator problem now, and if you think about an electron, right? And so the quantum harmonic oscillator is a very good solution to a molecule. And in a molecule, like you learned in chemistry, in freshman chemistry, you have Hund's rules to fill electrons in the energy levels. An atom or a molecule, right? So this is the electronic structure now of an atom or a molecule. And since electrons are fermions, right? So imagine electrons in an atom. Remember, our Hund's rules means that, yes, we want to put an electron in the ground state, but because of the Pauli exclusion principle, because there's fermions, they cannot be in the same energy at the same time. They can't be in the same place at the same time. We have to put another one here. Turns out electrons, like helium-3, have 2 spins, so you can actually put 2 in each energy level. Okay. Now, so fermions don't have this energy and momentum going towards 0 because you have all these filled energy levels. And so you don't get this macroscopic wave function, and you don't get a Bose-Einstein condensate, right? So a BEC, the Bose, is only for bosons. So what's the solution? The solution is that you want to, well, before I tell you the solution, let me tell you just back to helium-4 for a second. We said that this was a superfluid, and so actually you end up having a discontinuity in the heat capacity. So for helium-4, it looks like this. And one important thing is that the heat capacity goes to 0 as T goes to 0. That is, superfluidity in helium-4 is a second order phase transition, and so there's a discontinuity in the heat capacity. All right, so that's helium-4. Is it possible to make these things into fermions into a superfluid or a Bose-Einstein condensate? And the answer actually is yes. But you have to make composite bosons. So you actually have to make what's called a Cooper pair. So that's two fermions added together in some way, so paired up, which makes a composite boson. And so that's what happens in superconductivity. You get two electrons, they pair up into what's called a Cooper pair, and now those Cooper pairs can Bose condense and make a superconductor. So the question is, if helium-4 is a boson, can make a superfluid, if electrons can pair up and make a superfluid by making these composite bosons, so this is superconductivity. The question now is, can helium-3 form a superfluid? Okay, so let's stop there. I'll clear the board, and then we'll talk about helium-3 superfluidity.